Ionization energy is a periodic trend. First ionization energy is the energy it takes to remove that first, most loosely held electron from a gaseous element. You can also have a second, third, fourth ionization energy as you remove the second, third, fourth electron, etc. And it is a periodic property. We see that metals have low ionization energy and nonmetals have high ionization energy. The higher the ionization energy, the higher the attraction between the electron and the nucleus. So we're going to see that in a really, really small atom like helium, it's going to have our highest ionization energy, and a large atom like francium is going to have a very small ionization energy. So it's opposite. So again, high ionization energy with helium and a very low ionization energy with francium. Here's a periodic table that shows the actual values of ionization energy. And we can see as we go left to right, it does get larger as we go towards those nonmetals. And as we go up a family, we see it also gets larger as it goes towards that smallest atom, helium. What's happening is we're going across the period, we are adding a proton to each successive element, and that is increasing the nuclear charge. So nuclear charge just means the nuclear pull of the protons being attracted to the electrons, and we see that nuclear charge increasing as we go from left to right. We do see some differences, some things we might not expect if we think this periodic property is absolute, and it's not. There's exceptions all over the place. Here's a few exceptions. So let's look at beryllium and boron. We see that boron is a little bit lower than beryllium, and we can explain why this is by drawing the orbital diagram of both. Beryllium has 2 electrons in its 2s sublevel or 2s orbital. Boron also has that, but it has 1 electron in its 2p sublevel. So when we talk about removing an electron, we're talking about removing this one, and we're talking about removing this one. And in beryllium, we're removing an s electron. In boron, we're removing a p electron. And we see that the trend is that a p electron takes less energy to remove than an s electron does. And that's because an s electron cloud is a little bit closer to the nucleus than a p electron cloud. And so that causes a decrease in the amount of ionization energy that you need for boron. So again, p electrons take less energy to remove than s electrons do. Another situation that is a little bit unusual is between nitrogen and oxygen. And again, I can use orbital diagrams to show what's going on here. Nitrogen and oxygen, they both have a 2p sublevel. Nitrogen has 1 electron in each of those orbitals, and oxygen has 4 2p electrons, so it looks like this. So we are comparing removing this electron to removing this electron. And we see that removing this electron for oxygen is a little bit lower. And the reason why is because of an electron-electron repulsion. So because this electron is in a shared orbital, the other electron is going to repel it a little bit more, and so that means it takes less energy to remove it. Where if I remove that electron from nitrogen, it's going to take a little bit more in comparison because there's no electron-electron repulsion. So this just sums up what I was talking about. So as we go left to right, nuclear charge increases, and that pulls the electron cloud in tighter. That results in smaller atoms by the time we get over to the noble gas family. And then we do have some exceptions, an exception between boron and beryllium, so group 2 and group 3, and then a difference between nitrogen and oxygen because oxygen has more electron-electron repulsion, and so it doesn't take as much energy to remove its most loosely held electron. As we go down a family, you are increasing in energy levels. That means that the atom is getting bigger and bigger as we keep going down a family. And that is causing a distance between the nucleus and the most outermost electron. And so to remove that electron, as you go down a family, it takes less and less. Also, there's something called shielding effect. Shielding effect only applies to large atoms. So let's compare a really large atom to something really, really small. Maybe let's look at lithium versus francium. So francium has 87 electrons and has one outer electron, and then it has 86 core electrons. Lithium has 3 electrons. 2 of them are core electrons. And what happens with francium is those 86 electrons and all their energy levels here, they end up acting as a shield to block the nuclear pull. So the nucleus reaches out and has to go through all these electrons to hold on to that outermost electron, but those core electrons are shielding it. So not only do you have a greater distance, but you also have electron shielding. And so what that means is that it's really easy to remove that outermost electron for francium, which is a metal. Comparing to lithium, which is also a metal, one valence electron, no shielding. No shielding because this is just not a large atom. And so you're going to get that nucleus is going to hang on to that outermost electron more than it would with francium. Let's look at ionization energies for aluminum. So here I have aluminum here. This is my neutral atom, and we are going to rip an electron away. And I looked up the value of energy it takes to do this, and it takes 577 kilojoules per mole to do that. After I remove that electron, I have an aluminum ion, and that cation is going to be a little bit smaller than the aluminum neutral atom. And my diagram doesn't show that, but it does get a little bit smaller, and that's because the nuclear charge is the same, but there's just less electrons. So that nucleus is going to pull it in just a little bit tighter. Let's go ahead and take one more electron away. So I take that electron away, and I looked up the value for this. And so what do we see? We see that the ionization energy, so this one's the first ionization energy, and this one's the second ionization energy. We see that the ionization energy has increased. And that is because there's a difference between a p electron and then that second one, that's an s electron. So it just takes a little bit more. Let's remove the third electron, which is also an s electron. And again, I looked up the value, 2,750 kilojoules per mole. So that would be the third ionization energy. And I would go from having an aluminum 2 plus to an aluminum 3 plus ion. And notice what's happened here. Now I have completely removed all those valence electrons. So aluminum has 3 valence electrons. Now all of them have been pulled off. So I'm left with only the core electrons. Well, let's keep on with our chemistry torture and remove one more electron. And when I look up the value for removing this electron, I get 11,580 kilojoules. So I've had to add a lot of energy to remove that fourth electron, and that's because I am removing it from a full sublevel or a full energy level. Also, these are all the core electrons. So if I go to remove a core electron, it's going to take a lot of energy. There's not enough energy in a normal chemical reaction for this to occur. So this is a natural stopping point. So the reaction will remove 1, 2, and 3 electrons, but then it will stop. And that is because there's not enough energy to remove any core electrons or electrons from a full energy level. Here is a table of ionization energies. We can find those natural stopping points, and those natural stopping points, they tell us how many valence electrons there are, because it's easier to remove the valence electrons than it is the core electrons. So in bonding, only valence electrons are involved. So let's look at beryllium. So again, I'm going to look for a huge jump. That's going to tell me the difference between a valence electron and a core electron. And in beryllium, I see there's a big jump right here. So these right here, these are my valence electrons. And these two right here, these are my core electrons. So I can tell that beryllium only has 2 valence electrons because I can see them right there. Removed 1, 2, but then you don't remove those core electrons. Let's go to carbon. How many valence electrons does carbon have? 1, 2, 3, 4. We see a big jump in ionization energy. It goes from 6,000 to 30, almost 38,000. And there's not enough energy for that to happen in a chemical reaction. So we will see that carbon can lose 4 valence electrons, but then it will stop. Go ahead and stop the video and see if you can figure out what elements these are or what families they belong to, because valence electrons, it is a family property. So tell me what family would be element X, Y, and Z. Okay, we're back. With element X, I see there's a big jump right here. So this would be the carbon family. I could say that it has 4 valence electrons. I can say its oxidation number is +4. And I could also say that in the carbon family, everything ends in a P2. So that's all some information that I can get from this data. Let's look at the second one, element Y. We see the big jump after the 3rd electron. So this has 3 valence electrons. And looking on my periodic table, this is the boron family. I know that its electron configuration is going to end in a P1. And I know that it would have a +3 oxidation number. And last but not least, element Z. This is my alkali metal family. It has 1 valence electron, and my oxidation number is +1. So this is all the information that we can get from ionization energy data. So as a review, we get large jumps at energy level changes, smaller jumps at sublevel changes. So we know that p electrons take less energy than an s electron would. In chemical reactions, only outer electrons are affected, only those valence electrons are affected, because there's not enough energy to remove core electrons. It just takes too much energy. And the relative ease of which electrons are removed is related to what oxidation number the atom will have. Electron affinity is also a periodic property, and its definition is the amount of energy that it takes to add an electron to an element. And we know that nonmetals tend to want to add electrons, but metals don't. But we can measure the electron affinity of all the elements on the periodic table. There's no clear-cut trend, but we can still compare 2 atoms, especially 2 side by side. One thing that you should know, that if it is positive, it's not going to happen. So when we look at our noble gases, they all have positive electron affinities. So that means they are not going to add an electron. We also see positive electron affinities with other family groups. For example, these small atoms in the alkaline earth metal family, we see that they have a positive electron affinity. But we can compare it to lithium. So how come lithium has an electron affinity but beryllium doesn't? Well, you can use the orbital diagram to help you see this. So in lithium, I have a 2s orbital diagram, and it looks like this, only with 1 electron. And beryllium, it is filled. So if I go to add an electron to lithium, you can see where that's going to go. Okay, so there's kind of a place for it. But if you go to add an electron to beryllium, there's no place for it. It would have to go to a 2p sublevel, and that's just not going to happen. And so that is why it has a positive electron affinity. We can see the same thing with fluorine and neon. So fluorine, when you look at its 2p sublevel, we see that's almost filled, and neon, it is filled. So when you go to add an electron, you can see where fluorine's going to be. There's room for it, but there's no room for neon. It would have to go up to the 3rd s orbital, and that's just not going to happen. So that's why neon has a positive electron affinity, while fluorine, it can take an electron. Here are the last 2 families of the transition metals. So we can again compare copper to zinc. With copper, we see that we have a full 3D sublevel, but there is room in the 4s to put that electron. So that is why this one is positive. Zinc, that would not happen because everything is filled. Zinc already has that electron, and if you go to add one more electron, it would have to be put into a 4p sublevel.